Here we go. All right. Happy Tuesday. Oh, I see Edith has joined us. Welcome, Edith. Perfect timing. Okay, so it looks like a lot more than it is. The things that we're learning today, though, are some of the some items that carry over through the whole term, and they're pretty important foundational items. Today's lessons are pretty important. Now, 3.2. The first couple of things, finding our range is not super crazy hard, or I mean, I guess it's important, but it's like one or two slides. After that, standard deviation is a huge topic. It is something that we will be bringing with us, and the meaning behind it will be bringing with us through the whole term. And we'll be learning something called the empirical rule. Then in 3.4, 3.4 and 3.5 is a homework assignment together, so they tie together really well. We're going to talk about z-scores and quartiles. We're going to be dealing with median a lot here using the interquartile range. We'll talk about outliers and 5-number summaries and box plots. Then we will do lab 2. So it is pretty heavy, but it looks heavier than it is. So that's what we're going to be working on today. After today's class, you'll be able to complete the 3.2 homework, the 3.4/3.5 homework, and do lab 2. So all of that is going to be done today. It's probably one of our heavier days as far as how many sections we're covering, but there we go. All right, let's move on. So range is super, super simple and quick. It is exactly what you think it is. You take the largest data value and then you subtract the smallest data value. So you're just seeing what is the distance between the largest data value and the smallest data value. So something can range, like say all the participants in this class range from 18 to, I don't know, if let's say that everybody in this class was between 20 and 50, then we take 50 minus 20 and we would have a 30-year range. So it is just the largest minus the smallest, just seeing what the distance is between those two values. That's all range is. So our example here is the travel times that we were working with previously. So this is how long it takes people to get to work for this startup company. We just take the largest data value, which is 43 minutes, subtract the 5 minutes, which is our shortest data value, and we have a 38-minute range. So there's 38-minute difference between our shortest commute and our longest commute. That's it. That's all we're doing with range. And before I move on, I do want to say you will need your fancy schmancy calculator, your TI-84, if that's what you're using, or whichever graphing calculator you're using. I will be using a TI-84. You will need that today for sure. Okay. So standard deviation, this is a super important concept. Sometimes it causes a little bit of confusion. Hopefully, I will be able to explain it well. So what the standard deviation does is it tells us how spread out the numbers are in our data set. So we specifically use standard deviation when we're using mean as our measure of center. And standard deviation technically is the average distance each data value is from mean. So I would take the different the distance each one is from mean, and I would average that distance, and that would give us our standard deviation. So things about standard deviation is they're hugely affected by outliers, because if I have a larger one, I'm going to be calculating the mean of those distances. So we talked about mean before. We generally try not to use mean when we have big outliers. And so we won't see standard deviation as much when we have big outliers. But I am getting ahead of myself. So standard deviation tells us how spread out the numbers are. So once again, when we're dealing with population, we get the fancy symbol. This is a lowercase sigma. I'm going to be drawing it the entire term, and it's going to get uglier and uglier and uglier as I go. Now, this looks super complicated. I'm going to kind of give you a quick explanation of how to do this, and then we're going to walk through it step by step, how to calculate it by hand. Then I will show you how to use your calculator. So the way we calculated this by hand is you'd first calculate the mean. You take each data value, you subtract the mean from that data value then you would square it. Then you take the next data value, subtract the mean, and square it, and do this with all of them. Then you're going to add all of those squared differences together. You can add all of those together. Then you divide by the total number of data values you have. Once you do that, you take the square root. Don't worry, we're going to walk through it. And basically, you're not going to have to calculate it by hand after I teach you the calculator function. So it's really not that difficult. It is just time consuming. If I had a large data set, it's going to take me forever to calculate it by hand. And something about that is that it's easy. The more math you are doing, the more likely you are going to be to make a mistake. Something real important here is there are different formulas for population standard deviation and sample standard deviation. It's a different formula. There's one tiny little difference that's super important. So we're going to start with population. Once again, this lowercase sigma is our symbol, and and this is the formula. So I'm going to walk through it on the next screen. Okay. We are going to do one at a time. Now, we already had the mean of this data set, so I'm just going to super quickly get the mean. We already had it. I don't remember what it is, but it's okay. It's okay because I can calculate it again. Okay. My mean, I'm going to write it up here. My mean is 24.9. So we're going to use this 24.9 as our mean, and we're going to very slowly work our way through this entire thing. So I'm going to take each of these data values, I'm going to subtract the mean from it, and then I'm going to square it. So this is what it's going to look like. I'm going to do 23 minus 24.9 squared. That's 3.61. Take 26 minus 24.9 squared. I'm just going to do this with each one of those. If you're doing this along with me, please make sure to let me know if I make an error because I am the queen of typos. What essentially is happening with our, what essentially is happening is we are trying to eliminate negatives. That's why we square it, is because we're trying to eliminate negatives. The square root's going to happen later. Oh, see? You didn't even notice I made an error way up here. That should have been a 36. So I'm going to fix that. I just realized that I did that because I was like, I swear that 26 wasn't repeated. I apologize. Queen of typos strikes again. Okay. I apologize if I messed up your work by doing that. Just another example of your math teacher is human. Okay. Okay, so I took each data value, I subtracted the mean, and then I squared it. So these are my results. All of these on the right-hand column are my results. The next thing we're going to do is I'm going to take each of these results and we're just going to add them together. So I'm going to add all of these numbers together. I'm just going to see here. Let's hope I don't make a calculator typo. So my total, 902.32. If you're mathing along with me, please let me know if I make a mistake. Okay. So the next set, so that's what I did right here. Add the squared results. It says divide by the number of values in our data set. Our data set has 7 values. So I'm going to do 902.32 divided by 7. That gives me 128.9. All right, finally, the last thing we do is we take the square root. I'm going to do the square root of 128.9. That's going to give me a sigma 11.35. So my standard deviation here is 11.35. This tells me that the average distance each of our data values is from that 24.9 is 11.39 or 35 minutes. That is our standard deviation. That is our sigma. Now we're going to be doing a whole lot with standard deviation by the end of this lesson, but right now we're just going to calculate it and then pat ourselves on the back for doing a lovely job. So this is how we calculate that by hand. But I do not want you to calculate this by hand every time you work with it. Can you imagine? What if we had like 35 data values? Wouldn't that be a big pain in the rear? So thankfully, we have a calculator function, and we're going to do that next. Okay, hold on a second here. Previously, when I taught this lesson, I had my students calculate the next one. Wait, before I move on, any questions on this right here before I move on? Okay, good. So normally I would help you a little bit here and I would walk through it with you and then I would have you do this by hand. But what I would rather do is show you how to do this in your calculator. So we're going to jump to our fancy calculator because I want you to do this with your calculator. That is my goal, is to have you do this with your calculator and not by hand. You're more than welcome with small data sets to do this by hand, but ultimately, I want you to be proficient on your calculator. So let's jump over to the calculator. Here's mine. Yours may or may not look like mine, but it should be somewhat close and it will have the same features. Okay, so the most important thing to do first is to put our data into our calculator. In order to do that, you're going to use this button right here. It says STAT, really big right here, right next to the circle, it says STAT. So we're going to click on STAT, and then you want the top option. It's Edit. Hit Enter, and you'll get this screen. Yours might not be full. It might be full. It's okay whether it is or not. So you're going to get this screen, screen. Now I want to clear out all of my lists. These are list 1, list 2, list 3, list 4. Mine all have stuff in them. In order to do that, use the arrows on this circle to highlight the L1. So this circle gives you arrows. I want you to arrow up till you highlight L1. Then you hit clear and enter. The enter button's down here. Hit clear, enter. Do not hit delete. Delete will cause problems. We can fix them, but we would rather not have to. So don't hit delete. I'm going to do it again over here with list 2. I just use the arrows to arrow over to list 2. Arrow up to L2 is highlighted. Hit clear, enter, and it clears it out. I'm going to clear all of mine just because I like them all cleared out. Clear, enter. Clear, enter. Don't hit delete. Hit clear, enter. If you hit delete, I can help you fix it. Not a terrible deal, but it's annoying. So clear, enter is what you want to do. All right. Now I'm in list 1, and I'm just going to type in the data values for our test scores. So we have the test scores right here. I'm just going to type in these data values. Between each one, just hit enter. So put it 82, enter. 77, enter. And we're just going to go through all of these test scores and hope I don't typo. Always check them after you put them in because it is so easy to put an error in here. And you should end up with 10 of them. Let me give you a second to copy mine and I'm going to look at them to make sure I didn't typo. Okay, hopefully we're good and we all have our list in there. So now we're going to do fancy things with our list. This is super simple, hopefully. And I'm gonna go hit the stat button again because the stat button right here. And I'm gonna arrow over till calc is highlighted. So once again, let me get out of this. Hit stat, arrow over until calc is highlighted. You want the first option. This is one variable statistics. I have one variable and I'm looking for statistics regarding that. So one var stats. Hit enter. You'll get this screen right here. So the list where I put my things was in L1. Mine is already there, but let's pretend it wasn't, or let's pretend I was using L2. So take a look on the numbers here. Look at the blue. This is your lists, L1, L2, L3, L4, L5, and L6. These are my lists. So I want to tell my one var stats that my list is in L1. So those are blue numbers. Therefore, I hit the blue button, which is the second button, and then 1, and it gives me what's in that spot. That's what these colors are for. The blue ones, you use the blue button. The green ones, we use the green button. So these are blue, so I use the blue button. I am leaving frequency list. That's what this is. We're going to leave that blank and then go down to calculate. So L1, blank, and then calculate. I'm going to hit enter. And I have all sorts of really great stuff here. We're not going to go into every single piece of this yet. We'll do that later. But what I want, the information I want, my X bar, the calculator always assumes you have a sample. So instead of giving us mu, it gives us X bar. Even though, but remember, with mean, our sample and our population are calculated exactly the same way. Therefore, it doesn't matter. So our mean was 79. That's what we got the other day. That's perfect. What we're going to look at right now is this. This is that sigma symbol I told you about. This tells me that my population standard deviation, the sigma tells me that, is 9.8. So I'm going to write it on my paper on my screen. So it's telling me the standard deviation of this data set is 9.8. That's the average distance each data value is from 79 points or 79% or whatever is 9.8%. That's the average distance. This is our standard deviation. You look at the sigma. Yes, there's an X there. It's basically saying the sigma of my X values, because this is variable X, the sigma of my X values is 9.8. The standard deviation of my X values is 9.8. That's what it's telling me. Questions? Okay, I will go into what each and every field is later on in this lesson, but that's what I want you to get out of this particular time is just how to find that sigma. All right. And please use that instead of the doing it by hand. Please just do that. It's just a lot of work and you're more likely to make errors doing it by hand. So just use your calculator. Questions so far before I move on? All right. Let's talk about sample standard deviation. As I said, the sample standard deviation is going to look a little bit different. So it goes a little deeper than the explanation I'm going to give you, but I'm going to give you the basic definition or basic information because we don't need to go too deep here. This is an introductory stats and probability class. We don't need to go too deep. So the sample standard deviation is based on a sample. We saw with our mean samples last week that samples can give you very different answers as far as the mean goes can give you very different answers than the population. Because what if when I took my random sample, I ended up with just the three smallest numbers? Or what if I ended up with the three largest numbers? It could happen. It could be a sample of any size, of any of the numbers in the set. So a sample can be very different. Therefore, we try to account for that difference by dividing by one minus, or by the number of data values minus one, so one fewer. We call this degrees of freedom, but don't even worry about degrees of freedom until we get to chapter 9. We're not even going to worry about degrees of freedom till we get to chapter 9. Just know we're going to divide by n minus 1 instead of by n. So we're dividing by one less than the sample size. This will result in a little bit larger standard deviation because we are trying to account for this number isn't completely accurate because it's a sample. So that's the difference with our standard deviation, our sample. And because it is a sample, it doesn't get the pretty fun symbols. Instead, it just gets an S. A lowercase s is for sample standard deviation. It gets the boring things. Samples get boring things. So if you see an S, it's a sample standard deviation. We're going to calculate one of those. And it's going to be kind of weird because we're only using 3, and I don't like a size 3 sample ever, but it is what it is. All right. So I randomly took 3 of our employees from the 7 employee startup company. We're going to find the sample standard deviation. So the first thing I need to do is I need to find X bar. Remember, X bar is my sample mean. So I'm just going to take these 3, add them together, and then divide by 3. So my X bar is 22.3. Yep, good. Good, good, good. So now I'm just going to find the sample standard deviation of all of this. So I take each data value and I subtract the mean from it and then square it. So I will do 5 minus 22.3 squared. $299.29, then take 26 minus 22.3, square it. $13.69. Last, take 36 minus 22.3, square it. $187.69. Okay, so I took each data value, subtracted the mean, and then squared it. Now we're going to add all those 3 together. $500.67. Okay. Now we're going to divide it by n minus 1. So my n equals 3 because there are 3 data values. Therefore, n minus 1 equals 2. So I'm going to take 500.67 and we're going to divide it by 2 because that's n minus 1. Okay. All right. Finally, the last thing we do is you take the square root. So my S is going to be about 15.8. My standard deviation here is about 15.8. Now this is larger than it's larger than the standard deviation that we got in the previous. And a lot of that is because I believe it is. I don't remember what it was. I think it was 11 point something, wasn't it? Yeah. It's because I have, number 1, it's a sample. Number 2, we divided by n minus 1. And we have to account for that variability because we don't know what values we missed. This is especially important when you're dealing with super large samples and data sets. You don't know if you missed some really huge numbers or some really small numbers. So we have to account for that variability. We good so far? Okay. All right. Before we get here, I'm going to jump back to that screen, back to my calculator. So take a look at this calculator screen again. So this sigma x was my population standard deviation. Notice Sx is just a little bit bigger than that. Sx is the sample standard deviation. So your calculator doesn't know, do you have a sample or do you have a population? It doesn't know. So it's going to find both the sample and the population. So your homework will let you know if you have a sample or population. So you're going to have to determine which one of these to use. The fancy symbol, the sigma, is population, 9.8. The S, the weird super simple just letter SX, this right here is your sample standard deviation. It's 10.3. So when I divide it by n minus 1, so if I divide it by 9 instead of 10, I get 10.3. So make sure to write that down. At the end of this lesson, I'm going to go through and write down what we're going to write down what all of these are at the end because we're going to be adding some more to this screen, using some more things on this screen. So at the very end, we'll talk about what each of these things are, and you can, write them all down, and it'll be nice and helpful. All right. Are we good so far? So far, so good? All right. Okay, let's talk about standard deviation and how important it is and how we can compare things. So remember, we talked about previously when we were talking about relative frequency, we talked about kind of units and bringing it into the same units so we can compare things. We can do that with things like, well, right here, we're going to use it for waiting times at Wendy's and McDonald's. We can look at the standard deviations of two similar things, we can kind of compare them and say, okay, well, this one has a huge standard deviation and this one has a small, and kind of compare them and answer some questions. It's kind of it's helpful to compare those. So let's take a look at some data. So in my brain, these are drive-through wait times, but I don't know that they really are. But in my brain, they're drive-through wait times. So wait times at Wendy's and wait times at McDonald's. I'm not going to make you put these in your calculator or do calculations. I will do those for you. So the standard deviation for the Wendy's sample is 0.738 minutes. The standard deviation for McDonald's was 1.265 minutes. So what this tells us is that McDonald's has a wider range of data values. Their data values are more spread out than Wendy's because they have a larger standard deviation. Their wait times are more spread out. Wendy's are closer. So by looking at this, I can't tell what those wait times are. I can just tell you that Wendy's wait times are a little bit more predictable than McDonald's. Because the standard deviation is smaller, the wait times vary less from the mean than they do with McDonald's. With McDonald's, they vary more because it's a wider from the mean. I mean, I can go back and look at this and try to figure it out. I mean, look, McDonald's has this one's like 5 minute, almost 5 minutes. And I mean, they have a zero wait time in here. So that's probably why, is because they have a zero and they have an almost 5 minutes. Oh, there's another zero right here. There's a few of those. No wonder. But Wendy's they may not be, we don't know if they're better, but they're more consistent. So let's say that you're in a hurry and you want to be able to kind of predict, okay, well, I know that Wendy's is usually about 3 minutes and it doesn't vary a lot from that. You're probably going to go to Wendy's because you know it's going to be more consistent. Whereas McDonald's might be 5 minutes or you might get your food right away. We don't know. It varies a lot more. So it just shows you that it's more reliable. Make sense? Alrighty. Okay. I have never, ever, ever in my life used variance for anything other than answering questions in my stats class. But you will be asked for variance. You will be asked for it in a couple of homework questions. All variance is the standard deviation before we take the square root. All it is the standard deviation squared. So if you find a standard deviation, like in our calculator, I have the standard deviation right here. If I square that number, I get the variance. I've never used it for anything. It is not a number that I've used and been like, oh yeah, that's so useful. Never found it useful for anything. If you find something that makes it useful, you put it in the discussions because we would love to hear about it. I've never used it, but it has a name. It's called variance. So you just take the standard deviation and you square it, and that's your variance. That's it. That was exciting, wasn't it? That's it. I'm moving on. Okay. So this is important. This is something you are going to refer to and possibly draw 5,467.3 times. You are going to draw this a lot. I highly, highly recommend this picture on this page right here, printing it off and maybe stick it in like a sleeve and use a dry erase marker on it. Or this is something you're going to want to tab. You're going to want to keep this handy, or you can print off 8 of them and just keep using them. It's super useful. I've had a lot of people put them in sleeves and use dry erase markers. Super useful. All right. So the empirical rule is a really great way of estimating things. It's a really great way of estimating um, whether or not something is unusual or how likely it is to happen. It is a really great estimation. So it is not exact. So you see the word approximately there. So what I mean when I say something is within one standard deviation of a mean, it means that I take the mean and I add the standard deviation to it, and then that would be a data value or point on like a number line or a point that I'm going to remember. Take the mean, subtract the standard deviation from it, and then I'm going to have a range between that lower value and the upper value. And 68% of all of our data is going to be between that lower one standard deviation below the mean and one standard deviation above the mean. Now, if I added another standard deviation, so I take standard deviation, I multiply it by 2, and I add it to the mean, and then I get a number. Then I take the standard deviation times 2, I subtract it from the mean, and I get another number. 95% of my data is going to lie between 2 standard deviations from the mean. 95% of our data. Before I move on, I want to let you know anything outside of that is unusual and considered an outlier. Okay, I'm going to show you the drawing right here. So I'm going to give you a for instance here. You don't need to write this unless you want to. I'm going to make up numbers. Let's say that my mean is 20 because I like nice, pretty numbers. Let's say my mean is 20. So I'm going to say my mu is 20. Let's say my standard deviation is 5 because these are really easy numbers to work with. I'm going to add 5. So this would be 25. And then I'm going to subtract 5, and this would be 15. 68% of all of my data is going to be between 15 and 25. 68% of, like, I don't know how many data values I have. Let's say I have 500 data values, whatever. 68% of those data values are going to be in between 15 and 25. Now I'm going to add another 5. So this would be 30. Subtract another 5, and this would be 10. 95% of all of my data values are going to be within those 2 standard deviations of the mean. So 95% of all of my data is going to be between 10 and 30 in this case. Anything outside of this, so I'm going to highlight this. So this is all the usual data. This is all data that is not unusual. Anything outside of there is an outlier. So I'm going to put, I should have actually made that a pen. Anything outside of here is an outlier. I lost the I. There we go. Okay. Now, 99%, I'm going to add another number here. So I have 35 right here, and I have 5 right there. 99.7% of all of my data is going to be within 3 standard deviations of the mean. So 99.7% of my data is going to be between 5 and 35. Now, there's going to be other things. There's going to be some crazy numbers occasionally outside of there. Because we don't deal in absolutes, I'm never going to say 100% of my data is going to be between these two values. I'm not going to say that. But I will say 99.7% of all of my data is going to be within 3 standard deviations of the mean. But remember, 2 standard deviations is anything outside of 2 is where the outliers are, but 3 is going to encompass just about everything else. Like almost everything, 99.7% of my data is within 3 standard deviations.
May I ask you a question?
Of course.
Um, so you're just saying any data we get, whatever it is, will always work in this empirical rule. I mean, within the parameters you gave us. Basically, I mean, I'm just trying to wrap my head around it.
This is an estimation, and this is totally an estimation. But generally, because I mean, we try not to use mean and standard deviation when we have a skewed data set. We
Mhm.
try not to, because remember, we talked about that last week. If our data set is skewed, we generally go with median. If we have outliers, we generally go with median. This is a rule of thumb, and it is mostly true. It is not going to be true 100% of the time, but it is a really good rule of thumb.
Oh, for a bell-shaped.
Yeah, I mean it's
Okay, I get it.
for a
I get
bell
it.
shaped, but I mean it's a pretty good rule of thumb regardless. You just kind of you realize that this is an estimation because sometimes you just want to quickly estimate. It's kind of like if you're pacing off a floor trying to see how far it is, and you're just going to take steps and say, I know that this step is approximately 1 foot and you're pacing off a floor. You can get an approximate length of the room. This is an approximation, and it's a
Okay.
pretty good rule of thumb. So if
Okay.
that makes sense.
Yeah, yeah. I don't think I was thinking big enough.
Yeah. Yeah. I
Thank
mean,
you.
obviously, I'm going to teach you ways to do some exact stuff later on, but this is our estimation right here. And it really hasn't steered me wrong. I mean, because I'd be like, okay, well, look, this one is like a little bit above the mean, not quite a full standard deviation away. So this one is pretty usual. And this one, I just kind of use this as to get an idea. Is this unusual data? That's kind of what I use it for. Does that help? Okay. Now that my really ugly picture, I'm going to move on. All right, we're going to use it here. So the following data represents the serum HDL cholesterol of 54 female patients of a family doctor. So this is just some data. And we are going to label an empirical rule. This is one way that you're going to use it. This is the why I kind of recommend using a dry erase marker. This is a really great way with on your if you stick it in a sleeve and use dry erase or print off several of these. Okay. We're going to get the population and the mean and the standard deviation. Is this a population? It's probably a sample, but it says let's use the population mean and standard deviation. We're going to draw a histogram to verify bell-shaped, and then we're going to do some fun stuff with this. Okay, so my mean is 57.4. The standard deviation is 11.7. So this is mostly bell-shaped. See, it looks like it might be slightly right skewed, but it is mostly bell-shaped. So we kind of, as long as it's pretty close, and I mean, if it was shaped like this, I probably wouldn't use the empirical rule with it. But this one is, it's slightly skewed, but it's pretty bell-shaped. It's good enough. And if I draw a bell over it, yeah, that's an ugly bell, but it's pretty darn close. So we're going to call it bell-shaped. So what I'm going to do is I'm going to take my empirical rule picture and I'm going to label it. So the mean, this was the mean, was 57.4. So I took that 57.4 and I added 11.7. And I got 69.1. So that's one standard deviation to the right. I'm going to add another 11.7. And I got two standard deviations to the right. This one right here, add another 11.7, and I get this right here. So that is three standard deviations to the right. I'm going to go the other direction. I'm going to subtract 11.7 from the mean. This is one standard deviation below. Subtract another 11.7. I'm now two standard deviations below the mean. Once again, another 11.7. I am now three standard deviations below the mean. All right. So you're going to have homework questions where you're going to have to look at your empirical rule and figure out the percentage of people that are between two values. So what this is looking at, it wants to know what percentage of patients have HDL between 34 and 69.1. I'm going to highlight all of those. This section, and this section. I don't like that that highlighter makes it hard to read. So all I do is take the percents in each of those sections and just add them together. And I just add them together. Uh-oh. Well, it's 81.5. So 81.5% of my patients, of all patients, should have their serum HDL between 34 and 69.1. So if I'm a doctor and I want to know where do most of my patients lie, I'm going to be able to say, well, 81.5% of them are here. I mean, that's a good way to figure it, that approximately, I should expect approximately 81.5 of my patients to be between those two values. So looking at this, just in case you didn't get it, this section, these right here, these add up to 68. I just have one standard deviation above and one standard deviation below. I just split them in half. If I add this 13.5 and this 13.5, I get to 95. Then you add the 2.35 and the 2.35, it gets me to 99.7. There's the 0.15% in each of these tails. Don't forget about that because there's 0.3% that is outside of those three standard deviations. Okay, we're going to jump back to the screen that has the data. We want to know the actual. We want to see how close is our estimation. So I'm between 34 and 69.1. So let's jump back here. I'm just going to circle them all. If it's between 34 and 69.1, I'm going to circle it. Okay. Just going to circle the ones between 34 and 69.1. Okay. And then we're going to calculate that percent. Okay. All right. I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 45 out of 54 is what I have. Let's calculate that. 83.3%. That is not too far off, right? Because back here, we've got 81.5. 83.3% is not too far off. So once again, it is an estimation, but you will be using this type of math in your homework. So having that in a sheet or having several of those printed off, or you can just draw them. I mean, if you look at the one in your notes, you should be able to draw it, but seriously, printing a bunch of them off is helpful, or the putting it in the sheet protector. Super, super helpful. All right, questions so far before we move on? Okay. Okay, so we just finished section 3.3 or 3.2, sorry. Finish 3.2. You have enough information to do the homework on that. We're going to jump into 3.4. This is 3.4 and 3.5, this should say. They're together. They're one homework assignment, so I teach the whole thing together. And we're going to be learning about z-scores, and I love z-scores. And did I fix this? X minus mu. Okay, good. I had a mistake on this slide. It looks like I fixed it. Yay! Let's see how many other mistakes I didn't fix throughout the term. We will see. All right. So a z-score, we're still sticking with mean and standard deviation at the moment. So we're going to look at z-scores. Let me see what time it is. Okay, we're not too bad. So a z-score tells us how far a data value is from the mean in terms of standard deviations. So remember I was talking about if a data value is 2 standard deviations away from the mean, then it's within that 95%. So this z-score tells me how many standard deviations away from the mean am I. So the population z-score, these are calculated the same whether it's sample or population. It just uses different symbols. So you take the data value, you subtract the mean, and then divide by the number of standard deviations. There is no units to z-score, it's just a z-score. So it just tells you how far away from the mean your data value is. And this is super helpful when you're comparing apples and oranges, because if you have two different things um, that are similar but not the same, you can compare their z-scores to see which one is more likely to happen or which one is not as more unusual. We have a couple of examples, and hopefully this will be helpful. Okay, we're going to determine who's relatively taller. So what we're doing with z-scores is we're kind of converting them to the same units. So that the mean heights of males, the mean height of males 20 years or older is 69.1 with a standard deviation of 2.8 inches. The mean height of females 20 or over is 63.7 inches with a standard deviation of 2.7 inches. So we want to know which of these basketball players, which of these two people is relatively taller. So obviously Kevin Garnett is taller, but also their average height of a man is taller. And I mean, their standard deviations are pretty close, but the average height of a man is taller than the average height of a female. So we don't know who is relatively taller. So let's take a look. Let's calculate these z-scores. So let's start with Kevin Garnett. So remember, it is x minus mu divided by sigma. So I'm going to take his height, 83, minus the mean height. Then I'm going to divide it by the standard deviation. If you want to do this whole thing in your calculator, you need to put parentheses around your numerator. Otherwise, it will be bad, trust me. So I'm going to put this in my calculator. 83 minus 69.1 divided by 2.8. So my z-score here is 4.96. So remember, anything that is more than 2 standard deviations away from the mean is an outlier. Kevin Garnett is almost 5 standard deviations away from the mean. He is definitely an outlier. He is in that 0.15%, way beyond 3, but he is definitely an outlier because his z-score is greater than 2. So a z-score greater than 2 is an outlier. Let's try Candace Parker. So once again, x minus mu divided by sigma. So she is 63.0. Nope, she is 76 inches minus 63.7 divided by the standard deviation. Don't forget those parentheses if you put it all in your calculator at once. Her z-score is 4.56. But she also is very much an outlier because her Z-score is greater than 2, but she is still relatively shorter than Kevin Garnett. He is more standard deviations away from the average height than she is. Just barely, though. There's not a huge difference between a 4.96 Z-score and a 4.56 Z-score. They're both very tall, but he is relatively taller. Questions before you do one on your own. All right, next one's yours. Okay, so we have we're going to look at the Los Angeles Angels and the Colorado Rockies. We want to know which one had a relatively better season. The Angels scored 773 runs. Their mean is 677.4 runs. The standard deviation is 51.7. The Colorado Rockies are in the National League. Angels are in the American League. They scored 755 runs. Their mean is 640, and their standard deviation is 55.9. Calculate both of those Z-scores to see who had a relatively better season. I'm going to put this formula up here. I'm going to work quietly behind you and let you get a head start. So go ahead and calculate those Z-scores.
Hello? Hello?
Yes?
Oh, you hear me? Oh,
Yeah.
okay. I have a question, Professor. Do you guys have the video of the Excel PowerPoint? I'm kind of stuck with the class lower and class upper, and certain diagrams.
The video from last week is in on Blackboard.
Okay, I might have to request a day extension, because of like,
You,
um,
you can use a late pass that you can do that directly through you can do the late passes directly through your My Open Math assignment.
okay. I just want to make sure I get a pure grade versus like getting 20% off because you used it.
Nope, you don't lose points for using a late pass in My Open Math.
Okay, because I found it challenging to use Excel and I have a graph and
Labs are not accepted late at all.
okay.
So labs will have to be turned in tonight. If
Yeah,
you can send me a message through Blackboard. I'm going to get through this lesson right now, or you can stay after and ask questions that are off
I
topic.
will stay after the lesson because I really need help.
Okay. All right.
Okay.
Okay. So hopefully y'all get your Z scores here. We can see that even though the Rockies scored fewer runs than the Angels, you can see that their Z score is higher. They have a Z score of 2.06. They had an incredible season. Their number of runs was an outlier. The Angels, while they still did really well, they're really close to that 2 standard deviation mark. They're not quite an outlier. They still had a really great season because they're significantly above the mean, but the Rockies had a relatively better season. Any questions on that?
No.
Okay. All right, let's move on here. Okay. So go ahead and take mean and standard deviation and put them in your pocket. We're going to save those for later and we're going to jump into using median. So we've been doing stuff with, okay, we have a nice pretty bell curve. let's use our mean and standard deviation with the empirical rule. But now we're going to deal with what if we have, what if our data is skewed? What if we have skewed data? What are we going to do then? So when we're using the median, we use something called quartiles. So there's a whole lot of words here, but essentially this picture down here, if you're going to, in your notes, this is what I would put in my notes right here. If I was going to put anything in my notes, this is what I would put in there. So the median divides all of the data in half. It divides the lower 50% from the upper 50%. So we divide the data set into quartiles. So it's 4 equal parts. That's what quartiles means. It means we divided the data set into 4 equal parts. So what quartile 1 or Q1, we call it Q1, though it's quartile 1, what it does is it takes that bottom half below the median and it divides that in half. So 25% of my data is below quartile 1 and 25% of my data is between quartile 1 and the median. Quartile 2 is basically the median. We almost never call it quartile 2, almost never, but just realize that quartile 2 is the median. Quartile 3, it is halfway between the median and the largest data value. 25% of my data is between quartile 3 and that largest data value. And 25% of my data is between the median and quartile 3. So we have split our data up between or in 4 equal parts. That's what we do with quartiles. Now we're going to do some of this and it hopefully will help you to understand it. We'll be dividing these into quartiles and then we'll be doing some fun stuff with it. All right, let me move on. Okay, so here's how we find our quartiles. Just like we did with median, you arrange the data in ascending order, so smallest to largest. Then you find the median. So remember, the median is smack dab in the middle. It is halfway between. Then what you're going to do is you're going to find the median of the first half of your data. That's Q1. So you're just taking that bottom half of your data, the bottom 50%, find the median of that. That's Q1. You take the top half of your data above the median and you find the median of that. That's quartile 3. So we just take the median of the bottom and the median of the top. It's quartile 1 and quartile 3. We're going to do this with so this data right here, there's a construction zone and the speed limit is posted 25 miles per hour. So we took 14 randomly selected vehicles and we calculated their speed. So I decided that I didn't want to manually put these in order from smallest to largest, so I did it for us. It's smallest to largest right here on my screen, just because I didn't want to deal with rearranging it because I'm really bad at that and it's time consuming. So these are arranged smallest to largest. There are 14 of them. It's just important to know in our knower. So the first thing we're going to do is we're going to find the median. That's the first thing. Since there are 14 of them, the median is right between 7 and 8. Hopefully this is easy for you because you've done this in a homework assignment already and my pen is not working. There we go. So my median is going to be right here. Remember, I could do 32 plus 33 divided by 2. My median is 32.5. That's the median. All right, so now I need to find quartile 1. I'm going to use this bottom half of my data right here, and I'm going to find the median of that bottom half of my data. That's going to give me quartile 1. There are 7 data values below the median, so that middle one right here is quartile 1. This is Q1. That is my Q1. Now I need to find the median of the top to get quartile 3. Once again, there's 7 above the median, so I just find the fourth one. This right here. is Q3. Now, if I would have had an even number, like let's say it was 16 data values and I had 8 above and 8 below, we do the same thing with that center. You do the same, add them together and divide it in half. It's the same thing. So we found quartile 1, the median, and quartile 3. Now, all this is asking when it says interpret, all it wants you to do is to say 25% of my data is down here. 25% of my data is here. That was ugly. 25% is here and 25% is here. That's all it's looking for. It's not looking for anything fancy. That is the entire interpretation it's looking for. It wants you to say that 25% of my data is in each of those ranges. Questions? All right. And this part's like, you're like, okay, all that standard deviation stuff was really confusing, but I got this. All right. So yeah, this was the interpretation. Okay, so we're going to do this again. Once again, I already put these in order. I want you to try this. So the Highway Loss Data Institute routinely collects data on collision coverage. So this is claims against insurance, the physical damage of the vehicle, and we want to find all of our quartiles. So there are 1, 2, 3, 4, 5, 6. So there are 18 here. There are 18 data values here. They're already in lowest to highest. So I want you to go ahead and find the median and find quartiles 1 and 3. I'm going to give you a second. I'm going to let you work ahead of me. Yes, good job. I see in the chat. Good job. How we do? So the median, obviously, because we have 18 here, I had to go between 9 and 10 and add those together and divide them by 2 to get the 1805. And that left 9 below and 9 above. So I took the fifth one in the below and I took the fifth one in the above. There we go. Not too bad so far, right? We're okay? Right. Hopefully you're not scared yet. Let's move on. Unless there's questions? We're good? Okay. All right. So the interquartile range is median's answer to standard deviation. The interquartile range gives us an idea of how spread out our data is. So what we do is we take Q3 and then subtract Q1 from Q3. This gives us the interquartile range. We usually just call it IQR because interquartile range is a mouthful. So we just usually call it IQR, but it's just Q3 minus Q1. That's it. That's interquartile range. So for our speed data, for the data going through the construction zone, our Q3 was 38 and our Q1 was 28. So you just take Q3 minus Q1, 38 minus 28, and our middle 50%, the middle 50% of our data is there is 10. The range of that middle 50% is 10. So there's a difference of 10 between Q3 and Q1. We're going to be using the interquartile range to help us find outliers with median. This is median's answer to our 2 standard deviation away from the mean rule. So this will be median's answer to that. I know I told y'all to put that in your pocket, but I can't leave mean in my pocket. Okay, so I want to show you kind of the why here. So suppose we had a 15th car that traveled through the construction zone at 100 miles per hour, and I'm sure the police were hot on his tail. If not, I'm sure somebody reported him. So let's take a look at what happens to the mean before that car goes through the intersection or the construction zone and after. So without the 15th car, so with just our data set, our mean was 32.1. Once that 15th car went through, it jumped to 36.7, so it went up 4.6. The median, without that extra car going through, it was 32.5. Once that other car went through, our median just moved to 33. It barely changed. So take a look at standard deviation. This is where the big difference is. My standard deviation before that 100-mile-per-hour car was 6.2. Once the 100-mile-per-hour car went through, it moved to 18.5. It yanked that standard deviation way up there because now my data is super spread out. Look at how the IQR changed. It went from 10 to 11. It barely changed. That 100-mile-per-hour car is obviously an outlier. It's obviously very unusual. So it's going to skew my data. My data is now going to be skewed. So therefore, it causes big issues with mean. This is where median is good because this still gives us an idea of what happens through the construction zone, and that 100-mile-an-hour car doesn't mess things up so much. So once again, if it's symmetric, we're going to use mean and standard deviation. If it is skewed left or skewed right, we're going to use median and interquartile range. This is a really good rule of thumb. It's a really good rule of thumb here. Questions before we move on?
We're good.
Okay. All right. Okay. Now we're going to talk about how to find outliers using interquartile range. So when we find our boundaries, because, okay, let's jump back to mean and standard deviation. You can leave it in your pocket, but I'm taking it out of mine. So when we were using mean and standard deviation, remember that outliers were anything more than 2 standard deviations from the mean. And I was able to determine where the boundaries are of our usual data by saying, okay, so 2 standard deviations above the mean is this value, 2 standard deviations below the mean is this value. So all of my usual data, anything that's not an outlier, would be between these 2 numbers. When we're using median and IQR, median, yeah, and IQR, we call them fences. Those boundaries are called fences. So to find the lower fence, we take the take quartile 1, you subtract 1.5 times the IQR, that gives you my lower fence. Anything lower than the lower fence is an outlier. Then you take Q3 and you add 1.5 times the IQR, and any value greater than that is going to be an outlier. That would be your upper fence. We're going to do some math with this. This should be helpful. So our fences are the boundaries, that anything beyond those fences is an outlier. Okay. So let's take a look at the speed data, and then we're going to do the other one together. So my first and third quartiles for the speed data was 28 and 38. My interquartile range is 10. So I took my median, or those are my Q1, and I subtracted 1.5 times the IQR, and I got 13 miles per hour. Any cars going slower than 13 miles per hour would be an outlier. I take Q3 and I added 1.5 times the IQR, and I got 53 miles per hour. Any car going greater than 53 miles per hour would be considered an outlier. We're not including that 100-mile-per-hour car here. We didn't have any values that were smaller than 13 or greater than 53. So there are no outliers here. We're going to do the same thing with the collision data, but we're going to actually math this out together. So here we go. All right. My Q1 was, I wrote it down over here, 735. And my Q3 was 4668. So I'm going to find the IQR. So for the IQR, we take Q3 minus Q1, and our IQR is 3933. Okay. So now what I'm going to do is I'm going to find my lower fence. I'm going to take Q1, which is 735, and I'm going to subtract 1.5 times my IQR. So my lower fence, negative 5,164.5. I know that's weird that that's negative, but it does happen sometimes. So if the auto shop somehow owes you $5,164.50, then or anything lower than that, if they owe you a whole bunch of money, then you could be an outlier. So it happens frequently where the outliers don't really make sense. You just kind of go with it, just kind of shrug and say, that's silly. Let's move on. Let's go with our upper fence. I'm going to take my Q3, which is 4668, add 1.5 times 3933. That's an ugly 9. And I got 10,567.5. That is the upper fence. Any value higher than $10,567.50 is an outlier. We happen to have an outlier. We have a data value. We have a data value of $21,147. That is an outlier. Because it is greater than my upper fence, it is an outlier. Questions? All right, we're going to apply this. Hopefully this will be helpful. Before we do that, okay, I'm going to pause here for a second because you've had so much information going into your brain. So much information. I know this is the thing about summer classes is we have to put so much information into your brains in one night, and I know this is a lot. Just take a breath. It's all good. I'm gonna go grab my water. You guys go grab water. Why don't we just take 3 minutes, okay? Come right back because I feel like it's a good spot to just take 3 minutes. I'm gonna go get water and you all go get water. We'll be right back. I'm gonna pause this. So come back at 6:20. We're just gonna take a quick video or sorry, break.
Still have questions on how we got 21,147 as an outlier.
Because it's higher than 10,567. And that was our and that was our upper fence. We have our highest data value was 21.
Oh, so you call the high over what we
Yeah,
got for
because it was
one
higher.
quartile. Oh, okay. Thank you. I'll go get some water. Thank you.
Yes, go get some water. This won't let me pause it, so it's just going to keep running and I'll fix it later.
She said it can't.
Okay.
All right. Hope y'all got your water ready to go. Okay. Just felt like we needed a breath there rather than me throwing more stuff at you. Okay. So we're going to talk about something called a five-number summary. It's nothing different than what we've already done. It's just displaying things a little bit differently. So what a five-number summary does is a way to show the important pieces of your data. We use five-number summaries a lot of the time because if I had let's say I had a data set of 85, I don't want to write down all 85 numbers or look at this big pile of data the whole time. I just want the meaningful stuff out of it. So we use something called a five-number summary. It gives us just the meaningful pieces of our data and then throws everything else away, or at least sets it aside. So what the five-number summary consists of is the minimum, quartile 1, the median, quartile 3, and the maximum. We just list those five numbers. And with those five numbers, we can pretty much do anything that we need to do with that data set with those five numbers, because I can find the fences. I can determine if I have outliers. I can see what the median is. I can find the interquartile range. Anything meaningful I need to use do with the data, I can do that with the five-number summary. And that's really all I need. So I'm going to move and we're going to show the five-number summary for the highway loss data. Okay, the speed data, did I write that down? I don't even think I have that written down. I might have to go back because I actually have the highway loss data on my screen here. I don't have the speed data. Let me go back. I'm not going to go too far. Okay, I'm going to write it on my piece of paper or my, see. So my lowest, here's my minimum of my speed data, sorry. It's back here somewhere. My minimum is 20. My maximum is 40. My median was 32.5. Okay, 28. All right. All right. So when we write the five-number summary, you don't have to label what things are. Let me go back to that screen. Sorry if it messes with your eyes by me flipping through it like this. Okay. So you don't have to label them at all. You just write it down. If I know you gave me a five-number summary, I know that this is the minimum. I know this is Q1. This is the median. This is Q2 or Q3, and this is the maximum. Because you list them in order and you tell me it's a five-number summary, I know that that's what those are. You don't have to label them. You just write it down. If I ask you for a five-number summary, just give me all five numbers. You don't have to label them. So I'm going to write down the five-number summary for the collision loss data. My minimum, okay, I swear I wrote this down. My minimum is 180. Q1, 735. My median is 1805. Q3, 4668, and then the maximum is 21,147. That's it. That's your five-number summary. Now be really careful. There is a question in your homework where they give you a five-number summary, and it tells you below is the five-number summary, and then it asks you questions. So you have Q1, this is Q1, you have Q3. You don't have to do any calculations or find Q1 and Q3. They gave them to you. So be really careful. Realize that they didn't give you a whole data set. They gave you a five-number summary. So just read the instructions. All right. Questions on the five-number summary? We have 7 screens left and a couple of them are super fast. So we're almost there. We will be doing lab 2 though, so just letting you know. Okay, so last thing is we're going to draw a box plot. The There will be a box plot on your first test. You will have to draw one on paper in your first test. You'll you'll see as we get closer, I'll explain it. You'll learn how to, I will tell you how to submit your notes. Don't worry about that right now, but you will have to draw a box plot. So just letting you know ahead of time. So we are going to, first thing you want to do when drawing a box plot, now you don't necessarily need to do it in this order. Obviously, you're going to find your median, you're going to find Q1 and Q3. Then you want to find your fences because you're going to put your fences on in your box plot. You're going to draw a number line that's long enough to include your maximum and minimum values. So your number line is just a standard number line. You're not indicating data values in your data set. It's just a standard number line underneath your box plot. You're going to put a vertical lines for Q1, median, and Q3, and you're going to make a box. We're going to do this by hand. I'm going to do one from scratch for you so it'll make more sense. You're going to make a box. You're going to label your upper and lower fences. Then you're going to draw a line from the lower part of your box, which is where Q1 is, to the smallest data value that is inside your fence. Then you go from Q3, which is the top of your box, to the largest data value that is still inside your box. These are called whiskers. Outliers are going to be outside of your fences, and you're going to put an asterisk there. Asterisk represent outliers. I have a picture of one, and then we're going to draw one. Okay. This is our data about credit cards and interest rates. We don't really care what the data is, but there it is. It's all nice and pretty. All right. Here's my box plot. So notice underneath of the box plot is just a standard number line. We don't know what the data values are. Look back here. They all have decimals. I did not label the data values. I just made a standard number line that includes all the numbers in my data set. These right here are my fences. These are my fences. I guess it's just fence. This right here, we're not labeling these. You are not labeling these when you do these on your test. Do not label them when you do them on your test. I'm just labeling them for you so you can see where things are. Your box contains your interquartile range. It's from Q1 to Q3. The whiskers go to the smallest data value inside your fence and the largest data value inside your fence. My lowest data value is right here, but it is not in the fence. It's an outlier, so the whisker doesn't go all the way to it. The whisker goes to the last data value that is usual, that is not an outlier. This asterisk is an outlier. That's what that asterisk is. That is an outlier. We're going to do one of these together. Yes, sir. You have a question? You're on mute. I can't hear you.
So that line that comes from the box is like the tail that said the whisker and that doesn't go beyond. That's the set of the points, or is it the rectangle?
It is part of the points. The rectangle is
Like, I hope I explain myself because I'm stuck between knowing where the fence really is or if it's just the line.
the fences are these right here. These are fences. Those fences are not
Hello?
data values. Those are just defenses. We're going to draw one. We're going to draw one of these and
Mhm.
hopefully it helps. Hopefully when we draw it, it'll be helpful. That's what we're going to do on
Okay, so
the page.
so does this tail have any this little line that stops around 10 have any significance?
Yeah, it's a data value. It's this right here. This is the last,
Oh,
this is the last data value inside my fence. So
okay.
the number lower than that, this 6.5, that one's an outlier. So 6.5 is right here by an asterisk. 9.9 is at the end of my tail right there.
Okay.
We're going to do one together right here.
Thank
Okay,
you.
we're going to draw a box and whisker plot and box plot. either way, it's the same thing. We're going to draw one with our collision data. We're going to draw one together. I'm going to walk you through my process. So in the beginning, I drew this, had to draw it like 12 times to try to get the scale right. So I just know what the scale is because I've done this one a lot. So you're going to have to figure out what works for your data. So our collision loss data, it's really wide range. So I'm going to draw a very long number line and I'm going to count by thousands. So here we go. I'm going to go draw it all the way across here. And I'm going to count by thousands because I realize that that's what works best. I'm going to start, but I'm really going up by 500s, but I'm going to write the thousands. So like this. Because there's no way I'd fit all the numbers in here if I was trying to write all the numbers. I think I made these too small. Oh well, it's okay. Okay, so I know that I have to go all the way to 21,147. I don't think I have enough room here, and there would just be a big empty space. So I'm going to show you guys a trick. If you have a big space, so I have 10,036, and then my next data value is 21,147. So I have 10,000 between my last two data values. So we can do something called putting a break in the graph. So I'm going to do that. So this right here is putting a break in the graph. Basically what it's doing is saying I cut a big piece out of the center of my graph because I didn't want to do 12,000, 13,000, 14,000, 15,000, 16,000. I didn't want to do all of this empty space. So you can put a break in the graph right here, but you have to show it. You have to show that you broke the graph, that you took a chunk out of it. So that's what I did right there. So I'm going to pick it up with 20,000. 21,000. Okay. I think that I can just stop right there. Okay. So there's a big break in the graph, and then I have my highest values. So this works beautifully. Okay. Next thing I'm going to do, I'm going to change colors because I am just bored with my colors. So I'm going to change colors. Okay. Next thing I'm going to do is I'm going to indicate the median, Q1 and Q3. So my median is 1805. Right? Yep. So 1805 is right about here. That's the median. My Q1 is 735. So it's right about here. Q3 is 4668. So it's right about here. Now I'm going to draw a box around them. That's the middle 50% of my data is right there. So I drew, this is Q1 is at 735. Median was 1805 and Q3 was 4668. All right. Now I'm going to put my fences. We determined that the lower fence is a very big negative number, negative 5,164.5. My upper fence was 10,567.5. Now, just like I didn't want to, where's my words? Do a big, huge amount of graph all the way up to 21,000, whatever. I don't want to go super negative on my graph. It's kind of not important because I don't have negative numbers here. So what I usually do is just off the side here, this just goes below zero and I just put my fence down there. It's not going to cause any problems. You can just see it's a big negative number. Now the upper fence is a little bit more important. The upper fence was at 10,567.5. So I'm going to find approximately 10,567. There's my upper fence. Anything above that number is an outlier. Okay, let's do whiskers. The whiskers go to the last data value that is inside the fence. The lower one is easy. It's going to go to our smallest data value, which is 180. So it's just going to go, right there is good. It's probably a little too low, but it's okay. Nobody's going to judge me. My highest value inside the fence was 10,036. So I'm going to draw all the way to about 10,000. This is my last data value inside the fence was 10,036. Do not just draw your line to the fence. Do not draw it through the fence. It goes to the last data value inside the fence. Okay, we have an outlier. Our outlier is 21,147. So go approximately where that is, and I'm just going to draw an asterisk. That's my outlier. And this is it. This is your box plot. It is lovely. It is perfect. This kind of gives us a good picture of our data. Something super interesting about this, you can see that the whisker on the right is significantly longer than the whisker on the left. We can see that our data is skewed right because you see that super long whisker. If it was, the next page is going to give you everything else, but if it was symmetric, the box would be pretty much in the center of the whiskers. Before we move on to the final slide, any questions on my box plot? All right, you are going to need to draw one of these for your homeworks or for your test. It might be a good idea to watch this piece of the video again right before you take the test. This could be a good idea. And I'd be more than happy to if you send me a message and say, hey, about where in your video is this? Or just a second, I'm going to jump to, if you go into, let me get out of here. If you go into the week 2 materials, I specifically, the 3 point right here, where is it? This right here, the 3.4, 3.5 part 2, this is just the box plot stuff. Oh, sorry, it's taking you a second to get there. Okay. I'm going to wait till it catches up. I can see it on my other computer. So once you're in the instructional materials, in the 3.4 section here, there's a 3.4, 3.5 part 2 instructional video. That's just the box plot right there. So you can see that and just watch that if you want to watch that before the test. All right, go back here. Our last page of the instruction before the lab. Okay, you can see the skewed right, similar to ours. The whisker on the right is longer. Skewed left, the whisker on the left is longer. If it's symmetric, the whiskers are going to be approximately the same length. It's kind of interesting to be able to look at that and see how that compares to histograms. Right, so the only thing we have left is the lab. So any questions about what we just learned before we jump to the lab?
Ooh, the I had this saying, if everything is skewed, how do you read a graph? Like, because sometimes it had me count everything both up and down and then kind of like decimal it and then times it by a whole amount in order to get your result. How come?
Okay, I don't understand the question here.
This in regards to your skewed left or right, or is it like equilateral or something? Like equal for all of it? Why is it sometimes you have to you don't get an exact answer if you look at a bar graph, you get an exact answer if you uh multiply and then times it by a full amount. I don't really understand that point.
I'm still not quite understanding the question. So you might need to send me a specific question from the homework because I don't quite understand your question.
Mm-hmm.
For reading the graph, whether it's how it's skewed shouldn't matter on data values or how you read the graph. It just shows the shape of it. It shouldn't, the skew isn't going to affect reading the graph.
The homework was really interesting on this regard. It just
Okay.
was really interesting. It's
So
like I wish I could rephrase what I learned then and give it, but it's not coming quite out as what I wanted to
There's a
say.
message instructor button. Even if you're going back, if you can't, even though you can't still work on old homework, you can still go in and practice with it. So, and you can still ask me questions on it. So if you go into the old homework assignment, whatever question you were struggling with, if you click on message instructor, you'll actually send that question to me and you can ask me a question about it because I'm not quite
Okay.
understanding.
I have one question. Can I bring it up? Can I share it with you?
Is it on what we just learned?
Yeah, it's Excel. It's like on lower limit and upper limit.
On the lower the for the is it on what we just learned in today's lesson?
I suppose, yes.
It is on, okay, if it's on today's lesson, go ahead and ask.
Okay, let me share with you because it's still confusing me. It could
Okay, so
be that you're ahead.
I need to unshare my screen then, just a second.
Okay,
Okay, so as long as it's on today's lesson, I can answer it. Otherwise, wait until we're done.
okay, okay, let me see. Let me bring it up. It's this. Let me see, share. It's just I wasn't even really sure. Like I was doing this and then determine your interval width.
Okay.
And
Okay,
it was,
that's on the lab that's due today. That's not on today's lesson.
oh,
So we
sorry.
can,
I overshot
we
the runway
can
here.
wait until after I do the lab and then you can ask me about that.
Okay, no worries. Should I? Okay, I
Yeah, if
see
you
you.
can unshare, please. All
Yeah.
right.
Sorry.
Okay, I'm going to share again and we're going to talk about today's lab. Okay, so today's lab, you are using and wait till it shows that. Today's lab, you're going to use the continuous data from lab one. So lab one is due today. I will be grading those tomorrow. So that way, because they can't be turned in late. And so I will grade those tomorrow and that way you can get some feedback on them. If I take any points off at all, you will get feedback. So you're going to use your continuous data. There's a tool that we are going to need, and I forgot to turn that tool off. Uh-oh. I forgot to turn that tool off. I'm going to turn it off so that I can turn it back on again. Just a second here. Okay. And I'm going to show you two different ways to get the tool depending on what type of Excel you have, because I noticed that on my Mac, Excel is a little bit different than on my PC. So I'm going to share with you, show you on my Mac what to do, and then go over to my PC and show you. So there's a tool that we need called a data analysis tool. And it is super, super important. It can only be found on Excel. Numbers doesn't have it. Google Sheets doesn't have it. Only Excel has it. So that's why it's important to use Excel here. Super useful tool, though. A lot of people have used it in their final projects. And so I'm going to show you how you can get that. So I'm on my Mac right now. And I'm clicked on the tab up at the top. So we have all of these options up at the top. And I clicked on data. So over here on the right, it does not say data analysis. Because it does not say data analysis, I need to enable the tool. So in order to do that, I would click on analysis tools. And over here, I want the analysis tool pack. So you're going to click on that and it will enable that tool. So click on analysis tool pack and then OK. And now I have the data analysis tool and we're going to use that in this class. I'm going to stop sharing and then I'll share with my other computer. And I will show you on the other computer. Okay. All right. So now I'm on my other computer. Just give it a second here. There we go. I'm on my other computer. So this is on my PC. This is the most common way that you're going to see it because I have file up here and my other computer didn't have file up here. So I'm going to click on file and go down to options. Because let me show you what it looks like when I click on data. Okay. There's little box over here in the top right is empty. There's no tools there. I have some weird things happening. There's no tool there, it's just blank. So I'm going to click on File, go down to Options. I'm going to move slow because it seems like everything's moving slow. Go down here to Add-ins and click on Add-ins. It says Manage Excel Add-ins. Click on Go. I'll do this again after I do this. You're going to click on Analysis Toolpack and Analysis Toolpack VBA. And then click OK. And now Data Analysis shows up here. I'm going to walk through that one more time. Click on File. Go down to Options. Go to Add-ins. Manage Excel Add-ins. Click Go. And you want to enable Analysis Toolpack and Analysis Toolpack VBA, and then click OK. Everything from here on out is the same on whatever computer you're on, so I'm going to stop sharing and go back to my Mac. And I'll share from there. Okay. Okay, so now we're here. Give it a second to show up on my other screen. There we go. So now we're here. I'm using my continuous data, and you have this lovely little screen here. So I'm going to go click on data up at the top, and I want data analysis. So I'm going to click on this tool. And what I'm looking for, scroll down or scroll up. You want descriptive statistics. That's what we're looking for. Notice it says descriptive statistics right here. Descriptive statistics right there, and click OK. And you're going to get this pop up. My input range. The input range is my data. I'm just going to click on it and highlight all of it. Yes, I have a ton. You guys don't have as much as I do, just because I went a little wild. So my input range, just highlight it all. Output range. Where I want it to output, I'm going to move this. Where I want it to output is in this little box right here. So I'm just going to highlight the boxes I want it to land in. So you can, if you highlighted this whole thing, it's not a big deal. It'll just land where it lands. If you don't give it an output range, it's just going to open a whole new tab and it's going to be a pain in the rear. So go ahead and do your output range right there. We want summary statistics, so you need to check that box. So you do the input range, the output range, and summary statistics, and then you're going to click OK. Make this bigger. There's a whole lot of information in here. We don't need all of it, but there's a whole lot of information in here. It gives us the mean. Here's the median. Here's the mode. Gives us standard deviation. It gives us the variance. We don't care about variance. It's useless. The range, the minimum, and the maximum. Tells us if I added them all up, which I don't need. It tells me how many I have. It's a whole lot of really great information right there. This is why a lot of people use it in their final projects, because it does so much just right in this spot. So I want you to use your Excel tools for basically everything. You're using Excel tools. The point of the lab is for you to use Excel tools, and you'll be graded on whether or not you use them. So I'm going to show you how to use those. Okay. So this box right here is where I want the mean. So I want it basically to put this value right there into this mean box. Whenever we tell Excel to do something with numbers, we just put an equal sign ahead of it. So I put an equal sign there, and then I click on the box that I want it to populate. So I want that box to populate into there. So I put equals, and I clicked on that box and hit enter. It populates it. Here, it's the standard deviation. Hit equal, and I want it to give me this standard deviation right here. So I'm going to click on that and hit enter. I'm going to go back to 2 later. I'm going to leave 2 alone for right now. For the median, I'm going to hit equal. I'm going to go up here to median, click on this box, hit enter. The mode, once again, equal, go up here to the mode, click on that, hit enter. It's going to populate it for you. I'm going to leave 4 alone for right now. For my 5-number summary, this is going to be a little bit more tricky. Low and high and median are easy. Low, put equal. My minimum. High is easy, put equal. maximum. Q2 is just your median. So I can just do equal, and I could either do over in my descriptive statistics, or I could do that one. Quartiles, a little bit different. So in quartile 1, I'm going to hit equal. Start typing in the word quartile. It's really great because it tells me right here, my quartile. I want the quartile of this array. The array, I want to highlight all of your data. So for quartile, highlight my data, then put comma, and you tell it what quartile you want. I want quartile 1. So quartile, then highlight all your data, comma 1, close your parentheses. It'll give you quartile 1. We're going to do the same thing with quartile 3. Equals, start typing in quartile. It'll give it to you. Highlight all of my data. Okay. And then comma, I want quartile 3. Hit enter, close my parentheses. Bam, it gives you quartile 3. All right.
Excuse me. What
Yes.
is the difference between quartile INC and quartile EXC?
So what it's quartile EXC is excluding the mean or the median, and INC is including the median. I have not found it to give different answers either way. I don't care which one you choose. One includes the median and one excludes the median. And I've never had it give different answers. So you just choose whichever one you want.
Okay, thank you.
Huh? So this one right here, IQR right here, we're going to do math. And once again, to do math in Excel, you hit the equal sign. You're telling it, I'm going to tell you to do something. What I wanted to do is take quartile 3 and subtract quartile 1. So IQR is, click on this, click on that box, just type in minus, then click on this box right here, hit enter. You're just telling it to do math. You can see up here, up at the top on my, I can't make it go bigger. Up at the very top, my function bar, you can see what I typed in. See if you can see that on all of them. You can see it on, see, I used INC on one of them and I used EXC on the other. They're exactly the same thing, basically. So you just do equal. I'm going to do it again. Equals. I want this box minus this box, and just hit enter and it'll give me that. All right. So that's the stuff for the Excel. So number 2, it wants to know, do you have any unusual data? So what I want you to do is you're going to be calculating some z-scores. You can either use Excel to calculate those z-scores, or if you choose to, you can calculate them on your own. I'm not expecting you to be quite advanced enough or quite as advanced as you need to be to calculate the z-scores in Excel. If you want to, go for it. So there's 2 different ways that you can do this. You could either calculate, find out what values are 2 standard deviations above the mean and which values 2 standard deviations below the mean. So you have those boundaries and say, I have these numbers that are outside those boundaries, but you tell me what those boundaries are. Or what I did is I took the lowest data value I have and the highest data value I have, and I'm going to calculate the z-score. So I'm going to do low z-score. I'm going to type those words right there, and I'm going to use Excel to calculate my z-score. Watch how this works. So I'm going to click equals, and I'm going to do parenthesis, my lowest data value minus my mean. Notice I put parentheses around them because remember I told you if you don't put parentheses around them, bad things happen. The division sign is just that slash divided by standard deviation. And I'm going to hit enter. The z-score of my lowest data value is negative 2.4. Because that value is greater than 2 or beyond 2 standard deviations, that's an outlier. Let me give you a high z-score. So I'm going to do this again. Equals my highest data value. Go all the way down here. highest data value, okay, minus my mean, close my parentheses, don't forget the parentheses, divided by standard deviation equals. Look at that, I have an outlier on both ends. So both of those, both my lowest and my highest, are outliers. And I would type something in here about that. You just type it in here. My lowest data value of 4.4 and my highest data value of 9.3 are both outliers. If you want to do that, go for it. Or you can say, I don't have any outliers because my lowest data value has a z-score of this. My highest data value has a z-score of that. I'm allowing you a little bit of creativity there on how you do it. I am not requiring you to use the Excel tools to calculate the z-scores. Go ahead and do it on paper and then just reference it in here. But you need to give me the y and show me the numbers you got. Okay, let's go to number 4. What I'm looking for here, it says, given your mean and your median, what is the skew of your data? You're going to go into your Wayback Machine and look at last week, and you're going to talk about, are your mean and median close to each other, or is one greater than the other? So notice my mean is 7.047, my median is 7. Those numbers are super close to each other. Therefore, my data is bell-shaped. So I want you to just compare those numbers and say, my mean is much higher than my median, therefore, or my median is much higher than my mean, therefore. Look at your notes from last week. That's what I'm looking for there. I'm not looking for you to use this number right here, this skewness number. I am not looking for that. Do not use that skewness number. I want you to talk about the relationship between your mean and your median. That's it. That's the lab. So questions about this lab. I'm gonna
We can re-see this, right? We can actually look over the recording, right?
yes, I'm gonna post the recording hopefully tonight, latest tomorrow morning. And there's also, well, the video's for some reason not working right now, but I'm gonna fix it right after this class. There's a video in the week 2 materials also. So yes, yeah, you can rewatch it. All right, any other questions on this? Any other?
After,
Yes.
yeah, next week's past weeks with what goes on with this week. So I have questions of what I had earlier.
Okay, yeah, but any other questions on video for this lesson?
No.
Okay, anyone else? All right, I'm going to stop the recording. If I can find the button. There